Hello pre-calc. Hello calc. This is a lesson on the formal definition of a limit, which I've been avoiding up till now. It's very early in your book, and I prefer using the limit in several different ways before we go ahead and define it. But our day has come, so if you would, in your comp books, call this section definition of limit. And before I actually give you the formal definition, let's talk about it in an informal way. Here we have a function. If you would sketch a function like this, and the point A is indicated here, and I'm saying that the limit of this function as x approaches A is L. So the closer I get to A from the left and the right, the closer the value gets to L over here on the y-axis. When we're talking about a limit, we want to hit L. So it's like a target. So if we have an x near A, we should get a y near L. But how close is close? How near is near? Well, we want to establish an epsilon. And the letter epsilon looks like this. And I'm going to go within epsilon of L. And that means I can go up epsilon, so we get L plus epsilon. And we can go down epsilon, L minus epsilon. So I want to choose my x values wisely so that I get in the target area. Again, L plus epsilon and L minus epsilon. And epsilon can be as small as we want, depending on how important it is to hit near L. So we are going to have to be wise and choose our x values. Again, they're going to approach A, they're not going to be A. So we're going to take a range of values down here on the x-axis, which are going to use A plus delta. Delta looks like this. A plus delta, this is A plus delta, and this is A minus delta. And if I can establish a delta, a rule for delta, so that whatever values of x are in this interval, it will guarantee that the values for L are in this interval. Then I have found the limit L. So let's see if we can move over. Before I move over to the definition, let me give you a little bit more precise lingo that you're going to see in the definition, so we won't have so much a shock value. Turns out that when we're talking about being at A and going up A plus delta from A and going back A minus delta from A and establishing an interval around A, we can write that with an absolute value symbol. So all this can be stated mathematically as the absolute value of x. Remember, we're picking values for x inside this interval. We're approaching A from either side, and we have x, the absolute value of x minus A is less than delta. That is to say, that's the same way of saying x is within delta of A. So if you can carry that understanding of absolute value symbols, that's what this is saying. That's saying the difference between x and A is going to be less than delta. So x is within delta of A. Alright, keep that in mind, and let's do the absolute value for the limit and epsilon up here. So that would be another way to say that is the absolute value of the function. That's this value over here, f of x, which we read on the y-axis. F of x that minus L is less than epsilon. So that is to say, in plain lingo, that the function is within epsilon of L. Again, so absolute value symbols make it more concise when we start to say this formally. So, but when you see that, don't be shocked. Just think in your mind, this is saying the distance between the function and L is going to be less than epsilon. All right, I think that prequel is over. So let me give you the actual definition for a limit. And I have it written on the board over here. Let me see if I can line it up even better. All right, I think that shows up pretty well. Here it is, the definition of a limit. Let f be a function defined on an open interval containing c, and let L be a real number. Given those parameters, the limit as x approaches a of f of x equals L if, for every epsilon greater than 0, there exists a delta greater than 0, such that for all x, when x minus a absolute value is less than delta, then f of x minus L is less than epsilon. So I've given you a picture of that, and hopefully that is clear now. When we come to this, we're saying when when x is within a of delta, when x is within delta of a, that's what this means, then over here, f of x is within epsilon of L. So we have this dance. We're picking our y's closer and closer to a to establish what we need and are within epsilon of L. All right, let me show you an example, and it won't really hit home until you're able to do your own examples. So I'll do one and see if you can do one. Using the definition of limit, let's find the limit, or prove that the limit as x approaches 5 of 3x plus 2 equals what we think it is. So this is straightforward substitution. When we put 5 into 3x plus 2, we get 17. So now I'm going to use the definition of limit to prove that 17 is indeed the limit. To do that, I have to find a rule, a delta for any epsilon. No matter what epsilon I give you, you have to give me a rule for delta that will get me within epsilon of L. So here's how I'm going to do that. First of all, here's what's going on in our thoughts, which is probably the most important part. So this is sort of my scratch work. And I'm going to work backwards to find that there is such a rule for delta that will get me within epsilon of L. And here's how I do that. I'm going to start on this side. So putting it in, here's what I have to prove. Let me give myself a little bit of, according to this definition, this line, I'm going to restate this line in terms of this example. So when the absolute value of x minus, what's our a in this problem? We're approaching a, so it's right here, 5. So whatever we're approaching will show up there. When that is less than